Okay, guys, for our lecture for today, we're going to cover one of the theories of for dreaming that is probably it's actually one of the simplest, but the problem is that a lot of people tend to overcomplicate the idea, and so or at least be intimidated by the term. So it is a complicated theory. It's not an easy theory, but a lot of people get intimidated by the name of it. And so I like to go over this one specifically because it's really not as it doesn't have to be, you don't have to be intimidated by the terms. It's not as complex as you would think, just kind of from the basic side of things. And this is the activation synthesis theory of dreaming. And so Hobson and McCarley were the ones who created this or described this sort of model in the 1970s. And since the 1970s, this theory has undergone a lot of revisions, which of course happen with the increased knowledge that we have of the brain. So whenever we learn more and more about the brain, these kinds of theories that are physiological, that are brain based, that are neurologically based, tend to undergo a lot of revision and a lot of reworking because our knowledge of the brain is just constantly increasing with more and more research. And so really what it really boils down to is you have to understand what the term activation means and what the term synthesis means. And once you've gotten those terms down, then really the theory very simply speaks for itself. Now, of course, the model itself is more complicated and the details within that are more complicated. We won't get into those details in this class because we do cover quite a few theories on dreaming. And I want to make sure that everyone knows the basics of each major one. But really what it comes down to is activation of the brain. So areas of the brain are being used, and then we need to synthesize that information or process that information into something that makes sense. So this is kind of the basic of it. So it involves the premise that the REM-on area, which is located in the brainstem around the pons, is what is initiating REM sleep. And so it turns REM sleep on. And then we've talked about the brain in previous lectures, and there's a slideshow talking about REM-on, REM-off cells. One of the first series of lectures that we talked about the brain. So you can go back to the brain lecture slides to look at that, more specifically REM-on, REM-off cells and what areas of the brain are responsible for that. But when we have the REM-on area activated and initiated, what that's going to do is it's going to sort of start this whole thing. It's going to start the whole pattern, and then we're going to see REM sleep initiate. And so we know that REM sleep has particular characteristics. For example, particular EEG waves that you see, these beta waves while a person is in REM. You also see that muscle paralysis and the rapid eye movement, so the eye movements back and forth, that is indicative of REM sleep. Now, during REM, this is a period of sleep that, of course, we are cut off from the outside world. Now, we are not necessarily cut off in the sense that we are there is no input whatsoever, but we are cut off in the sense that we do have a lot less input coming in. Now, when we talk about the brain being isolated, remember that during REM sleep, the body is paralyzed. And because the body is paralyzed, it is not receiving input from the environment like you would, for example, something touching you or, output and you touching something. And because there's this particular isolation that happens, the brain is in a state where any kind of input is going to receive will be internal. And so our brains want to process that, okay? So when you're awake and you're alert and you're looking and you're touching things with your hands, you're getting input in to your brain. You know, if you're touching a pencil or touching a pen, you're getting an input into what that feels like, the texture. Is it cold? Is it hot? Is it, you know, soft? Is it hard? And that input is going to be processed by other things in your environment. When you cut that sort of that main avenue off, then your brain is still going to work and it's still going to do things. But now it's in this kind of isolated chamber, and now it's got to process that information that is going on in the brain without the input-output regular pattern that it would have given you were awake. So when we look at this in terms of the theory, we have the activation part, right? So the activation part is, remember that, you know, there's an old myth that people still really believe today, which is, it's unfortunate, but there are people that say, we only use 10% of our brain, or the brain shuts off when we sleep. And both of these are very, very untrue. We use all of our brain all of the time. We use different parts at different times, but if we don't use a part of our brain, it'll die. You know, it won't work anymore. And so when we're asleep, there are just different systems that are working. Now, they may be the same systems that are working when we're awake, but they may be working differently. And so there's still activity, there's still things happening in the brain while we sleep. It's still working on things, right? But it may just be in a different way than when we're awake. Now, when we do magnetic resonance imaging, or MRI, or more specifically functional MRI, we are looking at the blood flow in the brain. And so it goes on the theory that our brain needs blood in order to work. Because when you exercise and you use these storages of fat in your body, you burn that to produce energy. Well, the brain does not have fat stores. There's no fat in the brain. So the brain can't use stored up energy to work. It has to get energy as it's working. It has to, as it's burning energy, it needs fuel immediately. And it gets its fuel through blood, which carries oxygen and glucose, which the brain uses as energy. It converts to energy, and that's how that's how the cells function. So the idea is when you're doing an fMRI, when you're in an fMRI or doing an fMRI scan, your brain, whatever parts is what we call activated or showing activity, or we also call it light up, but that light up is essentially a fancy analysis. Colors. When we say that it's active, that means that it's physically using more blood. More blood is being transferred to that area. And that is what we say that's activity. So if you ever hear that term, you're not really quite sure what it means. Activation just simply refers to that part of the brain is being used. And we assume that because there's more blood flow going to a particular area, then that must mean that it's being used. So a lot of this information that we're going to talk about from the activation synthesis model comes from these fMRI studies, and it comes from the results from which we've been able to determine that yes, more blood flow goes to these areas during these times. So when we look at the brain asleep, these systems, these same systems that work when we're awake, they're acting a little bit differently, okay? They may work in reverse, they may work in different order, but we see this sort of different configuration in REM sleep. We see a different configuration in non-REM sleep, And we see a different configuration when we're awake, because our brain's only so big and we only have so many neurons, but all of these are sort of linked together into a network, into a system. So even though you might have billions of neurons and hundreds or thousands of systems, these systems can work differently given different circumstances, different situations, and different configurations. So in the case of working when you're asleep versus working when you're in REM sleep, non-REM sleep, to when you're awake. So these particular areas that are activated, okay, of course include things like awareness, eye movements, instinct, vestibular sensations, which is, where you are in space and how you're moving, as well as memory consolidation and emotion. So we know that these things are occurring, these systems are being activated while you're in these sleep states. So interestingly, if you think about dreams, you can certainly dream and feel a certain way. You can be sad in a dream, which is emotions. You can be angry. You can be scared in a nightmare or a bad dream. You can feel like you're flying. You can feel like you're falling. And those would be vestibular sensations. You can feel where you are in space feels differently, or you can feel yourself walking. Again, all vestibular sensations. Of course, memory consolidation is what we think is one of the purpose. It's a major purpose of sleeping, for us to take what we learned from the earlier in the day and consolidate it to long-term memory. And of course, we go over the things that we've learned that day, the things that we've done that day and days previous in our dreams. We also see that there are a lot of things that occur during our dreams that feel very familiar, okay? We also see motor activity or activity in the areas of the brain that are responsible for our body movements and for motor activity. And so the output is blocked because you're paralyzed, but the input is generated within your brain. So you're getting input, but you're needing to, and there's activation happening. There's neurons that are being sparked, right? But your brain needs to now take all of that information in, and it needs to do something with it. Now, activation is very important. So activation is all the areas of the brain that are currently active, that are working, that are the neurons that are firing, the networks that are active. All of these things are important, but what's not active is also very important. So these areas that either have reduced activation or have been deactivated and don't work the same or aren't working at the time are areas like sensory information, the areas of the brain that process sensory information, and the prefrontal cortex. So the prefrontal cortex's job is to make sense of all of this and to tell you that it's not real. Your prefrontal cortex's job is to say, okay, you're flying now. This can't happen. That's not logical. You're in a dream. And so because this prefrontal cortex is quiet during sleep, we're not getting the feedback that this isn't real, which is why some people have very vivid dreams, why some people tend to, when you're in a dream, you tend to wake up and you go, wow, I didn't even know that I was dreaming, and I didn't know that was what was happening, and it felt right and it made sense, even though you go through, like, for example, a very story-like dream, and yet you see somebody that looks like somebody but they're in a different body, but you think, I know that person, and it kind of makes sense in the moment. But logically speaking, when you go back over your dream, you realize it might have been very illogical. So when we have these areas of activation, we have to do something with it. So our brain is constantly filling in gaps. When you are awake and alert and you look outside your window and you look at your environment and you're driving your car and you look outside and you look at everything around you, your brain cannot process every single tiny little detail that it sees. So it fills in gaps. It wants to see the world as a whole. It wants to be able to take all the information that comes in and process it or synthesize it in a way that makes sense. So when you're dreaming, you have all this activation happening, and your brain wants to take this information and process it or synthesize it in a way that it knows how to do and that makes the most sense. So the synthesizing part of this is essentially taking the activation and synthesizing it or processing it in a way that makes sense. So this, where we see this kind of idea that, okay, even though this dream is a dream and you're flying or you're, I don't know, at Hogwarts and you're playing Quidditch, it feels real. You feel like you're there. You feel like it's happening, right? And these areas of activation, like the emotion areas of the brain and sensory information that you're getting, the vestibular information, all of that needs to be processed in some way that makes sense. And it's synthesized in a way that you're going to experience it the way that you know it. Because that is how your brain is going to process it. It's not going to process it in a new way. It's going to process it in a way that makes sense for you, because that is how your brain synthesizes the information. So that's those areas that are activating that are emotional based, sensory based, vestibular based. You're going to process that into anger, sadness, feeling like you're floating, feeling like you're walking, like you're running, or like you can't run, like you're stuck in a particular place. And so, you're also seeing activation in the cerebral cortex, whereas where we see all this network of memories happening. And so you're pulling information that you've previously learned or information that you know about from your lifetime. So a dream can really access any pre-existing information, pre-existing memory. So maybe you're dreaming about your grandmother. Maybe you're dreaming about your teacher. Maybe you're dreaming about homework. Maybe you're dreaming about something that you haven't thought about in a while. All of these things are accessing pre-existing memories, which is why, and when it comes to dreams, nothing is off limits. If you've thought about it, if it's in your memories, then it's fair game for dreams. If you have activation in the areas and the networking of memories where that belongs, then you're probably going to experience that in a dream, if you have that activation while you're dreaming. Now, it doesn't always mean you're going to remember that, but you're going to synthesize it in the way that makes the most sense to your brain. This is why we often see that there are aspects of your life that will get pulled into your dreams. If you're going through a very stressful time, you might experience the emotion of anxiety. If you're going, a lot of times people have reoccurring dreams when school begins. For example, you might dream that you're in your pajamas in your classroom, or you go to the wrong class, or you've been in the wrong class the whole semester, and you might have these reoccurring dreams that are brought on by stress for starting a new semester. A lot of times you're going to notice that your dreams mean something to you specifically because it's your brain and it's your memories and it's your emotions and your experience. And all of these things make sense to you. And even though it may not feel logical when you think about it, there may be elements that seem to make sense to you, even though when you try to explain it to somebody else, it doesn't necessarily add up. So this last part right here, this idea is that, dreams are your interpretation, your brain's interpretation of how it synthesized all of those activated areas. So that's a really important key point here. So in the activation synthesis model, what they're saying is that dreams are your interpretation of the synthesis or processing of the activated areas that are activated, that are occurring while you're in REM sleep. So here's a really very simple, sort of schematic. You can see at the bottom here in the pons, This is where the REM-on cells are, and they sort of start the system. They start the REM sleep, which then those networks of neurons spread out to all over the cerebral cortex, to motor areas, to sensory areas, to the limbic system to get emotional areas for emotion, and the cerebral cortex for that network of memories. And this system kind of goes to all the other systems and activates those. And then your brain is synthesizing that into essentially a dream. Now, of course, there's some criticisms with this theory. One is that it's super neurological. Of course it's neurological. It's all brain-based. And some say it's just too neurological to describe dreams. Okay, there are people that just really don't feel like it gets at what dreaming is. The majority of this work is based on animal research. And so, of course, even though the animals that we study have a very similar nervous system compared to humans, there's always that element of they aren't humans, and it could be something else, and it could be different. We do have evidence that animals dream in their sleep. But we don't have anything definitive to say that absolutely yes, we can't prove it. We can only provide evidence for things like, looking at in cats, cutting particular areas of the brainstem to get rid of the paralysis that occurs in REM. And so when they're not paralyzed in REM sleep, it looks like they're acting out their dreams because cats will engage in particular behaviors like batting at what looks like maybe a butterfly or a bug. And we see in humans, of course, we see something similar happen when there's damage to the brainstem where they will act out their dreams. So we can have this sort of, research that aligns to say that it's very likely that animals dream. And since their nervous systems are so similar, for example, cats and rats and mice and dogs are, nervous systems are so similar to humans that we can say that, perhaps this is the same thing happening. And also non-human primates, there's a lot of research in that. But we can't definitively say for sure because all of this work is primarily based in animal research. We also find that there seems to be that instead of the instigation or the initiation of dreaming happening in the brainstem, which is the activation synthesis theory, we have some fMRI evidence that suggests that the initiation actually starts in the cerebral cortex. So the activation synthesis theory states that it starts in the brainstem with the REM-on areas, that initiates REM sleep, and then those networks move up through the cerebral cortex. Whereas our fMRI evidence seems to suggest that it actually might begin in the cerebral cortex, not in the brainstem and the REM-on areas. We also find that there are people who have REM sleep but simply don't dream, and that people dream in types of sleep that aren't REM sleep. So, this would argue that it's too limited, that the activation synthesis theory can only really work if you only dream in REM sleep. So there are some criticisms to this theory, and I think what you're going to find is none of these theories by themselves do explain dreaming in a way that gives it justice. And I think that you're going to find, just like in anything, in development, in any other field of work, you have tons and tons of theories that try to explain one thing, but usually not one theory does it justice and does a good job of explaining everything. So really, the best thing to do when looking at something like dreaming is to look at these theories and say, hey, let's not have all these individual theories. What parts can we put together to make a more comprehensive theory that seems to get at what dreaming really is? And it might just be a consolidated set of theories. Now, some of these theories, of course, contradict one another in some areas. So activation synthesis being a very neurological theory, if we look at some of the more Freudian psychoanalytic styles in terms of, or fields in dream theories. They're very different. Some of them are contradictory and much less neurological. But I think that you're going to find that no one theory can absolutely explain it all. And really, you have to kind of squish some elements together to get at a really good, solid theory to explain everything. So if you have any questions, of course, you can put them on the question forum or send me an email. And hopefully this is a good explanation for activation synthesis, because most students tend to confuse this one and just don't really get this one as well. But as you can see that, once you understand what the terms mean and kind of put it all together, the overall arching idea is relatively simple, but the detail in which this theory goes into, of course, is much more complicated. But I just want you to understand the basics of this. So let me know if you have any questions, and good luck in your exams for this week.